So again, let's review the code here. With the array to implement wedge graph, after we have all the constructors implemented, we look at add vertex, get the node or the vertex, and add into that array location. Num vertices is just index of array, start from 0, and increment it. Now, after you add to that location, you want to initialize edges to 0. So that's why we just loop through all the indexes and initialize to 0 for the two-dimensional arrays every time you add. Now, we also have to do add edge, right, after add vertex. Now, add edge is depending on from vertex, to vertex, and wedge. So this is two-dimensional arrays. We need to know the location of from vertex, which is the index of it. Because if you know the index of it, then we can map to the row and columns, right? Row is just the index of from in vertex, and column is the index of to vertex, and then we put a wedge there. To implement index is, so we just do index is to get the index of that vertex. Pretty much just iterate to the array, and once we found the information is equals to that location, then we keep increment that index and return it from 0 to plus plus. Then we get the index. So that's how we add the edge. And wedge is, if you want to see what's the wedge from vertex to vertex, then we just use get the index of form and get the index of to vertex, which is row and column, and return the edge at that location. Get two vertices, get all the adjacency, right? Adjacents of the vertex or vertex. So we create a collection. We use Q to get, which is you use call it adjacent vertices. Now we need to know the index of the vertex, which is form. Once we know form, we can just iterate to the whole array list, that array to all the graph here, all the vertices, by starting edge from index and initialize that to index to 0. 1 is not equals to no edges, not the zeros. 1, then we know that we found the edges, then we add into NQ of all the vertices to index and return the adjacent vertices. Alright, so now this is pretty much a UML diagram for wedge graph interface using the array. We can use the linked list implementation. So a linked list that identifies all the vertices to which a particular vertex is connected. Each vertex has its own adjacency list. So we look at two alternative approaches. We can use an array of vertices that each contain a reference to a linked list of nodes. Or you can use a linked list of vertices that each contain a reference to a linked list of nodes. So we're going to use the same example. So this is the first approach. We set an array of vertices, and the array also links to the list of node or edges. So you may see that we're going to create a node that has the index of adjacent vertex with the wedge and the reference to the next edge. So this is an array of nodes. store, right? I'm sorry, this is just an array, actually an array. Array that contains the vertices and reference to adjacent nodes or adjacent vertex, which is point to index of that vertex. Like lambda points to Houston and links to the linked list of edges, which is weight 800. And from Houston to Washington is 600. So let's check. Atlanta to Houston 800. Atlanta to Washington is 600. Yes, so it has to be like Atlanta to Washington, not from Houston to Washington, because this is a linked of all the edges for Atlanta. And happen to the rest the same. So the second approach is create a linked list of vertices. The node of the vertices has the vertex info, which is the city name, a pointer to the next vertex, and also have the pointer to the edges. Okay. So that's how we're implementing it. So you we don't have the code for that, but you pretty much know this is just a simple linked list with a node. So you already learned how to do that. Then you pretty much can create that like linked list of linked list right there. Graph applications. So where do we use the graph? So like we've seen so far that we didn't look at the traversal yet. The traversal itself could be the application of the graph. So the basic operations allow us to implement different traversals independent of how the graph itself is actually implemented. So there are two types of graph traversals. The strategy of going down a branch to its deepest point and moving up is called depth first strategy. And that strategy way to visit each vertex in the tree is to visit each vertex on level 0, then each vertex on level 1, then each vertex on level 2, and so on. So visiting each vertex by level, this is called breadth first strategy. So there are two types of strategy to do traversal. So let's look at example that we said these are the cities that the airlines will fly to with its own weight. So can we get from Austin to Washington? Yes. So what are the traversal strategy that we want? Now we're going to look at just two, which is the breadth first and depth first. Again, depth first means you go depth into get to Washington, like Austin to Dallas, Dallas to Denver, Denver to Atlanta, Atlanta to Washington. That's called depth. Another depth path is Austin to Houston, Houston to Atlanta, Atlanta to Washington. That's a second depth path. You get deep until you get to the destination. This is called depth first strategy. But breadth first is you go Austin to Dallas, Austin to Houston, and from Dallas we say Dallas to Denver, Dallas to Chicago, and from Houston we say Houston to Atlanta, and from Denver we say Denver to Atlanta, Denver to Chicago. This is called breadth. We're not reaching Washington, but we're spreading out. For each node has to visit all the vertices first. And then we go to Atlanta to Washington. Now we know that that's all the path that we can go. Okay, this is called breadth first. So we already understand that. Now we're going to look at the algorithms. How we going to do the depth first. So the first approach that we try, we said we want to do depth first, deep until we get to destination, right? Start vertex and end vertex. Like this case, we said Austin is start, end is Washington. And we said, is there a path from start to end vertex? Returns Boolean. If there is return found the path. So start found with false. If there's no path, we return false. We can use stack to help. We push the start vertex and use the loop. Do look at the top, right? Stack top equals to the vertex. Just initialize something to hold the value at the top, and then we pop if vertex equals to the end vertex. Then we say we found, right? Because we want to go to Washington, right? From Austin. So we push Austin, and then we look at the top. Vertex is Austin, right? Because we push Austin. So we pop. Now vertex to Austin. When we pop, it's empty, right? We said Austin equals to Washington. No, then we do else. Else that means put our adjacent vertices onto the stack. So what are the adjacent vertices? Austin, we have Dallas and Houston. So we push Dallas and Houston into the stack. Right, so while the stack is not empty and it's not found, then we go back. So we say we have what? Dallas and Houston. So look at the top. Okay, let's say Dallas we push Dallas and then push Houston, then Houston is at the top. So Houston is vertex. Then we pop out. So now stack has only Dallas. But we check Houston equals to Washington. No, then we push out adjacents of the vertices onto the stack. Adjacent to who? Houston is Atlanta. That's it, right? Houston one adjacent is Atlanta. So Atlanta push back into the stack. And go back, stack's not empty. Then we do top again. Now we got Atlanta. So we start to go to depth, right? Instead of breadth. So we get Atlanta. We pop Atlanta out. We say vertex equals to end vertex. No, Atlanta is not Washington. That's not true. We get adjacent of Atlanta, push into the stack, which is Washington. Right, we have Washington. So we push Washington into the stack, right? But the problem here, you see that adjacent to Atlanta is not just Washington, but also Houston, right? Okay. I mean, it seems like we have to go back, and if we don't mark it, Houston is already visited. You see, we forget to do mark. It's going to go back and visit all the Houston again and again. So this is going to be an infinite loops. Correct? Because we push Washington, we put Houston and pop Houston and do it again. And push it back and do it again, right? So we have to fix this to make sure that if vertex is not marked, that's it. Just one keyword that, hey, Houston is marked. We visit this way, we've seen it.